Okay. We're getting up to Byron's area. Antennas. So we got transmitters and receivers. So we need to connect them to something. So we have what they call the isotropic radiator, which is the theoretical antenna that you measure other antennas against as a reference. The isotropic would generate a spherical radiation pattern in all directions. You can't build one. I'm not sure that I guess the end of a wire might be sort of close, but it's basically a reference. And we reference other antennas to it in decibels relative to an isotropic. That's dBi. Okay. You'll see here when we talk about half-wave dipoles, sometimes they'll reference it to the half-wave and it'll be a decibel relative to a dipole or a dBd. So one of the simplest, what you see on AM broadcast stations are quarter wave vertical antennas. On AM broadcast, because of the frequency, they're down at what, 160 or below meters?
What,
AM broadcast?
Yeah.
They're very high antennas. But they use verticals because they're omnidirectional. And they want to send their signal out, they broadcast it to everybody. So that's why they don't use beam antennas.
That's maybe it's Voice of America or someone like that.
Next is most common probably in ham radio is half-wave dipoles or variations of a half-wave dipole. Dipole means there's two poles. It's got two elements that are basically opposite polarities of the signal. Sometimes use it as a reference, dBd. It's claimed to be 2.15 dBi more than an isotropic. That's theoretical. Now, because of ground reflection, it's actually more like 6 dB. Unless, of course, you've got a half-wave dipole in free space, which means, miles up in the air. And then it's only 2.15 because there is no ground reflection. But nobody has a half-wave dipole in free space.
I didn't realize that the ground reflection gain was that much. That's a lot.
I just watched the Dave Castor video on that. And he showed a bunch of examples that he modeled, and it was anywhere from, depending on height to the ground and inverted, anywhere from 5 to 6 dB.
So inverted this way? Or?
No, inverted V.
Yeah, okay.
Was less, but not that much. That was the thing he did. He did it even 60 degrees.
Okay.
Which you're not supposed to do.
Yeah.
And it was still only maybe a dB and a half less than the straight wire half wave.
Interesting.
It was surprising. Said it surprised him. Okay. And he's been teaching this stuff for years and years. The half-wave dipole, there's kind of three variations. The normal one you see is center fed, where the elements are equal quarter wave lengths. There's an off-center feed. The antenna is still half wavelength long, but you feed it at 20, 30% from one end. It varies. There's different, you get a different impedance match depending on exactly what point you pick.
And the difference between the off-center fed and center fed and in fed is what harmonics it'll operate on. So if you have a center fed, I believe it operates on even harmonics.
Right.
If it's off center fed, it operates on odd harmonics. If it's in fed, it works on all harmonics. All harmonics.
Yeah, that's one of the benefits of an in-fed is you don't have to do a lot of traps and other things. You can pick up, if you had it 80 meter in-fed, which would be 3.5 megahertz, you're going to get 7 megahertz, 10 megahertz, whatever, 4 times 3.5, on up in
Yeah. If
in
you
3.5 megahertz.
if you do it 80 meter through 10 in bed, you've got all the bands without a tuner above 80 meters. Yeah.
I'm about to put one up and see. I have a center fed fan dipole right now that definitely is more than 6 dB greater than my vertical.
In some directions.
Yeah, but it seems to be all directions. Remember, I'm probably more closer to 90-degree inverted V.
Mm-hmm.
So it's fairly omnidirectional. It's slightly oblong. And because it's pointed a little bit east of north, I get sort of over the pole stuff, and Europe is a piece of cake.
Well, I was thinking of as far as your low angle radiation, within maybe 1,000 miles, your band dipole is going to do the majority of the work. But for further than that, your vertical may be doing the job better, but only you would know because you see the signals.
Well, I can switch back and forth on FT8, and it does better on everything.
Really?
Really.
Okay.
I'm thinking about taking the vertical down, putting something else up.
Yeah, it's not doing you well.
Okay, and then we have beams, which are sort of modifications of half-wave dipoles. The most popular is a Yagi Uda, named after the 2 Japanese guys that invented it. As I understand the story, it was actually Professor Uda that did the work, but he worked for Yagi. So Yagi got first name.
Yeah.
Then there's the log periodic, which is similar but different. And then there's quad antennas, which are loops.
Well, the log periodic is your typical, TV
antenna. The beams have high gain and narrow bandwidth. So it's just a compromise of the more gain that you want to try to get out of an antenna by squeezing the radiation pattern, the narrower the bandwidth is going to be.
The quad gives you a little bit more gain than the Yagi. And the reason for that is that you're working with, a half-wave radiator, with the Yagi, and with the quad, you're working with a full wave loop. So, but after probably about 7 or 8 elements, the difference.
Yes, diminishing returns. Yeah. Actually, they claim it's probably not worth it after 5.
Yeah.
You're better off stacking them, and you get 3 dB by putting 2 of them up. And it takes probably 10, 12 elements to get that 3 dB just by adding them. And plus, you get a very long boom. Or you can even put 4 of them in a quad array, get 12 dB increase over the total. Okay, quarter wave verticals work off of ground reflection. Normally, if it's just a straight quarter wave element up in the air, they use radials, which is just an array of wires insulated from the ground that reflects the signal, and that's where you get the gain, part of the gain, maybe as much as 3 dB or so due to that reflection.
There's some good studies on counterpoises versus radials. And usually a counterpoise, you can get better efficiency, than a ground radial system with it's a few wires that you're working with.
Because in essence, if you look at it like in this picture, it's a vertical half-wave dipole, but one of the elements is this imaginary element in the ground. So that's what you're going to reflect up. So the more efficient your radial or counterpoise is, if it's just real high in the air, part of the shield of the feed cable could act as the counterpoise. So it could be your other element. Over here are some examples of different lengths, whether it's a quarter wave, a half wave, and so on, and what the radiation patterns look like. For a normal quarter wave vertical, this is a cross section of the vertical radiation pattern, because it's really just a torus donut sliced in half, because that's where the ground is. If it was in free space, it would be a complete donut. And as that gets longer, or more wavelength, you see how the pattern changes. We get a lower radiation angle by going to a half wave, and we go to 5/8 wave. It's lower yet, but we're starting to get these more vertical lobes, so part of your power is going out there. And then on 3/4 wave, you're mostly vertical. And then full wavelength, you got nice lobes, but very high radiation angle. Wouldn't be good for long distance. And then when you really get up there, then you just get this mess of stuff. Okay, here's a half-wave dipole showing kind of the radiation wave, which is partly showing the polarization. And you see that it's what we're sending is the E field. Okay, when you put a signal on the antenna, you actually generate an E field and an H field, the magnetic field, which will be perpendicular to the electrostatic field. What you normally are receiving and transmitting is the electrostatic field. So if you notice, it's varying along the element. So if that element is horizontal to the Earth, that's what we call horizontal polarization, because the waveform is varying horizontally. Even if you rotate this around to where, because this wave is all the way around it, even if it was shown vertical, it's still going back and forth in a horizontal direction. Right. If we rotate the antenna vertically, okay, now I've got that waveform going up and down vertically. Even though it may be going all the way around 360, it's still vertical, so it's vertical polarization. A typical half-wave dipole in free space, which is higher than most people have one, is going to be 72 ohms. As it gets closer to the ground, the impedance lowers, or if you angle the elements down like an inverted V, you lower them even more, you may get down to 25 ohms. So the impedance is going to decrease as the height decreases. Test question. This is showing the free space radiation over on the right. You got a big donut, and we have no radiation along the axis. So it's directional in that it's broadside to the wire or the element. And this on the left is a cross section of that, just showing the lobes.
And that,
Now that
at your NF and HF, that's never really true. Because you still end up getting a little bit off the end.
yeah. Yeah, this theoretical stuff and the real stuff are close, but not the same. And as you get closer to the ground, this gets modified a lot. It's easier to show these nice symmetrical ones. Okay, we have an off-center feed, sometimes called a Wyndham.
Wyndham is usually, well, technically it's going to be a parallel that off-center dipole.
What do you mean?
Parallel line like window line,
Oh,
ladder
okay.
line. And the third is,
Yeah,
classic Wyndham.
but it's still half wavelength long, and instead of in the center, you're feeding it at a point, from what I understand, in the 20 to 30% range. It varies depending on what impedance you want.
Flavor.
Kind of directional.
You get different harmonics than you do with the center fed,
And
and your impedance is easier to match because wherever they've done it here, they're saying it's 235 to 270. So with the right kind of balun, I can get close to 50 ohms, so I have a good match.
yeah, most those will, if it's a 30%, they'll give you a 4-to-1 balun. If it's 20%, they'll give you a 5-to-1 balun. And I think the only one who's really doing the 5-to-1 balance a lot is Chameleon.
But the benefit isn't directional, it's still omni.
Well, it's the same sort of pattern.
Yeah, the pattern then,
It's broadside to the antenna. The radiation angle is going to be affected by how high it is off the ground. And for most of these, the optimum is half a wavelength.
I'm just trying to figure out why it's not in the center if it's not directional.
yeah,
Typically, it just.
Well, remember, your wave is still going to be resonating like that. Doesn't matter where you feed it.
at least on the lowest one.
Well, I mean, it affects the impedance and harmonics, and then your current is still going to be like that. So you got maximum current in the center. You have no current at the end because there's nowhere for it to flow except for end effect. But in theory, there's no current at the end.
I was trying to figure out why it wasn't.
So-
And when you feed it at the middle, which is the highest current point, that's going to be the lowest impedance.
So when you grab your antenna and the minimum RF burns, you grab the middle or the end?
It's a good question because the end is very high voltage and no current until you grab it. And then I suspect the high voltage is going to create a current through you. And what they call an RF burn, which is bone deep. Okay. So when we have an end fed, we normally feed it with a balun or unun. I guess it's actually an unun because it isn't balanced. And it's still a half wavelength antenna. You're just feeding it different, and you get different effects as far as the harmonics that it resonates at. And also the impedance is going to be very high. So you're going to use a 49 or 64 or something to one transformer. They'll be ununs technically because they're unbalanced to unbalanced.
if you do a parallel bed wire, ladder line or window line, loss from mismatch, high SWR is very low. And so, you can be very agile, frequency agile with the antenna, as long as you have a tuner that'll, handle the mismatch.
Now, on this off center, if I pick my point, where my cursor went there, just right, I can get this to say 350 ohms impedance. So I could feed it with a 350 ohm twin lead.
Yeah.
It comes in 300, 450, 600. Yeah.
Mhm.
And it's much lower loss than coax. Although you still have to have a matching transformer before you got to your receiver, because you got to get it back to 50 ohms.
Yeah.
I've been for a while.
I've had fun with those.
Okay, the famous Yagi Uda. It's a multi-element directional antenna. It consists of a driven element and usually only one reflector. And then additional, what we call directors. And the way it works, as I understand it, is you get a reflection of the signal from the driven element, and the spacing between these two is such that, because there's a 180-degree phase shift on here, when it reflects back off of the reflector, at some point it comes in phase with the signal off the driven element, so it adds to it. So you get that portion of the wave reflected back, just like the same effect with the vertical and the ground reflection. It's the same kind of thing, and it adds to the signal, and it decreases the signal going this way in the reverse. So that's why you have a very small radiation lobe on the back end of a beam antenna. Then these additional driven elements are spaced such that they add more to it, and it's a very complicated formula, figuring the spacing for all of those and the length. The driven element on the Yagi is going to be approximately a half a wavelength. The reflector is going to be 3 to 5% longer, and each one of the driven elements is going to be a few percentage less as you go down. Okay, kind of like a log periodic, where they get smaller as you get farther from the driven element. Here's what a radiation pattern for a Yagi looks like. So you see that we have very small side and rear lobes. They're in this chart. They didn't label it. Typically 20 dB down. And over on the right is an elevation pattern. And you can see it's a very low radiation takeoff angle, is what they call that. The blue lines are a dipole, a half-wave dipole at the same height, and what the difference in pattern would be. And you can see on the dipole, it's bidirectional. You don't have anything along the element, but broadside to it is where your maximum radiation is. And then we have a quad. And like Byron said, these are full wavelength loops. Now, they don't have to be square. They can actually be any shape. It just affects the polarization a little bit. But basically, where you feed it determines whether it's horizontal or vertical. If you feed it on the bottom, then it's horizontally polarized because most of your radiation is on the upper and lower elements. If you feed it on the side, it's vertically polarized. So if you were to make it, say, a rectangle, much taller than it was wide, and you fed it on the side, you'd have more aperture for a vertical radiator. A lot of times they'll be crossed and you'll see it as a diamond, but it's still sort of the vector thing. It's either horizontal or vertical, depending on which corner you feed it with. And we talked about polarization, where it's defined as the orientation of the E field with respect to the Earth. That's a test question. So if it's horizontal to the Earth, it's horizontally polarized. If it's vertical, it's vertical. If it's bounced off of the ionosphere, it's elliptical. If it comes from a satellite, it's probably circular. But we're not talking about those today.
Or if it's Nimbus, it's actually circular.
Yeah. Yeah, when you get to reflections,
Nimbus.
it changes.
You're vertical.
Yeah.
Oh,
Anytime it's reflected off of things, it affects the polarization. And then, of course, when you got a satellite that's rotating, it's changing vertical, horizontal. So a lot of times for satellite antennas, they'll have crossed Yagis so they can receive it either way.
this is kind of off topic, but this 5G stuff that's going on, and then finally come out,
Yeah.
is that horizontal or vertical?
Most said I would imagine to be vertical, but
I think, although they're patch antennas, so I'm not sure. I don't know much about them. They're magic.
always
When you get into the gigahertz stuff, that's a whole different world.
the the weekly ham radio broadcast. What they're saying that they're doing regular cell phone 3G and 4G satellites that can pick up the cell phone, but they're arraying like 1,000 dipoles on the satellite. I'm thinking, how are they doing that?
It's small.
Yeah. It's all printed circuit boards. Yeah.
Yeah, when I was doing some consulting with the Air Force on some classified stuff, there was a radar system called flap lid. It was about 6-foot diameter circular platform that you could raise or rotate. In other words, azimuth elevation.
Yeah.
It had 1,024 dipoles on that were phased. So you could phase shift the beam depending on the phase shift to the antennas. We didn't make it, by the way. Okay, so we got transmitters, receivers, and antennas. We need to connect them with something. We call them feed lines. Most of the time we use coaxial cable. It's relatively cheap. It's common. It was invented to reduce interference from other signals because it maintains the electrostatic field within the cable between the center conductor and the shield. There's a number of variations. Amateur radio is almost all 50 ohm. TV would be 75 ohm. Occasionally, you might see that used as a matching transformer to an antenna, where you can do some magic quarter wave stuff, and it matches most of these coax that's going to be used, like in your shack, is going to be RG58 or 8X, which are like 1/4 inch diameter. There's some other smaller ones. These are probably the most common. Probably 8X is becoming the most common because it's flexible, relatively cheap, it's easy to work, pretty good shielding.
So
And if you're only doing short runs, you don't care about the loss that much.
I saw DX Engineering has a flexible LMR 240,
Okay.
and that's a little bit more efficient than the 8X. It's a little bit thinner.
And a little bit more expensive.
Yeah.
That's the other trade-off on all these things is cost versus. When you get into the 1/2 inch sizes like RG8 and LMR 400, they're much stiffer cables. Even though there's an ultra-flex version of LMR 400 that uses stranded center conductor, so it's not quite as stiff. The straight LMR 400 is very stiff.
Yeah. And where does the 316 fall in between the 8U and the 400?
I believe the one that's missing off of my board,
Yeah,
or no, that's 213 was the one that fell off.
213. Yeah.
I don't know if I had the other one up there or not. And the 6U and the 59 are the 75 ohm that you see in TV. Whoops. Then we also have 2-wire, where you have your normal TV twin lead, which is 300 ohms because of the separation. It's like 1/2 inch. You have open wire, where you got 2 wires separated by spacers similar to this ladder line. And I think that's like 600, normally 600 ohm. You have window line, which isn't shown. And that's, I believe, like 350 or 450 range. It's like a wider twin lead with holes cut in it called windows.
Yeah, most of that I think is 450.
And they are lower loss than coax, but they do radiate and also pick up interference. So everything's a trade-off. Any questions? Discussions? What did we forget?
So I
think so.
question, when you put a mast up, so I'm assuming because we're in such a lightning prone area that you'd want to ground both the mast and use a lightning arrestor on the coax side, right?
Well, you normally put a lightning arrestor where your feed line, whatever it is, enters your shack, your radio room, whatever you call it, where your radio is. And you'll want to have a good ground system to connect that to, that's tied into your facility ground. And it's probably not going to be close. So you need to run a ground line from where your facility safety ground out by your service entrance is. And there'll be a ground rod there. And you need to connect that up with wherever your ground rod is, just outside your shack entrance. If you really want to do it right, if that's a long distance, you probably want to put another ground rod every 10 feet or so along the path, because the effective area of a ground rod is about 8-foot radius.
Okay.
So the more ground rods you have spaced that distance apart, the better connection to ground you have. And the ground we have around here, according to a chart I recently saw, we're
Let's get
somewhere between 4 and 8 on that chart, which is not great, but better than Colorado.
also been fun whether it's rained recently or not.
You can, if, bringing the line down on your mast, you could put a lightning arrestor in the ground at the base and tie it to a ground rod at that point. Particularly if it's a long distance from where your shack entrance is.
Okay.
Probably alleviate a little bit of the stray current if it caught most of it right there.
The other thing that's a good thing to do is get an antenna switch that, like the Alpha Delta, that shorts the connections out. So when you don't have one of the ports selected, they're grounded. So it would discharge, particularly with a vertical antenna. You could get some static buildup. And if that's going connected directly to your radio, you could actually get enough static buildup to cause a problem. Whereas if you got it through a grounding switch, when you're not using it, you discharge the static to ground.
And if you're Dave Lorette, you have one at the bottom of the antenna. You have one at the where you enter the building, and then you have a restaurant also on the inside too. On your big, ground bus.
But also,
You'd have a halo on the top and bottom
All
too.
connected to your antenna.
But
Yeah,
every time you add
also,
you're adding resistance.
okay,
Wide.
go ahead.
I'm saying if you add multiple arresters, aren't you adding resistance to the line?
No more than a connector, because all they are is, in most cases, it's some sort of spark gap, usually a little gas discharge tube. So there's no additional resistance other than like a barrel connector.
Okay.
So compared to the loss in the line, it's going to be fairly insignificant.
Got it.
However, it doesn't matter how many of them you have or where they're at. If you have a direct strike, all bets are off. So the lightning arresters and the grounding, help discharge potential lightning, which is the way, if you've seen a lot of the facilities that have lightning arresters on the peaks and the corners all tied together with grounds, those are to dissipate the charge before you actually get a lightning discharge. So they help, but they don't 100% prevent it.
Right. Okay. Thank you.
Did I answer your question?
You did.
so if you take a wiener and you wrap your ground wire around it, will you have a cooked wiener after the lightning strike?
You may not.
Wrong.
Guys.
Go ahead.
The weird thing, with lightning is that the stuff is polarized. If you'll notice that on the power poles, it's about 3 feet off the ground, they have a little loop coming out. And if you see something that's been damaged by lightning, like coax, you'll see holes, ever so far in the same polarized plane.